I still not able to prepare another 1 minute.
Yeah, there was still some, like, 1 minute of preparation left, right?
Yes.
Yeah, okay, I'll give you another minute. Ah, okay, it works with truck. Okay, thank you very much. Yeah, I was about to take a shot, so that's excellent. Thank you.
Hello everyone, I'm Dr. Lu from China, and today I'm going to do the report of problem number 8, Sci-Fi sound. Here's my content today. First, I will introduce my experiments, introduce the key phenomena and analysis. Then I will introduce my theory, followed by experimental verifications. And here's the problem review. Tapping a chemical spring can make a sound like a laser should in a science fiction movie. Investigate and explain this phenomenon. And the keywords here are tapping, chemical spring, and laser should. For tapping, I define as a short time impact which will make a pulse in the chemical spring. And for chemical spring, we use slinky spring in my experiments because it can generate a laser should-like sound easily. And for laser should-like sound, here is our two examples from the Star Wars movie. And I will define it afterwards. And here's parameters are defined. A is the length of cross-section, B is the width of cross-section, and R is radius slinky, and rho is standing still, E is Young's modulus, and G is shear modulus. And here's my experiments. And I discuss this problem in two parts. First, slinky slings horizontally, and then slinky places vertically, shown in the picture. And here's my video for experiments. Or you can see the sound afterwards in my. And this is spectrogram I observed when slinky slings horizontally. This is one sine sound, and you can see the signal is disturbing and periodical. And if you let the slinky vibrates freely, you may hear periodical sound, the large period. And when slinky places vertically, you can still hear disturbing sound in this signal graph. And if you let it vibrate freely, you will still hear the rest of sound. And which means the larger period. And here's analysis. I found the fundamental frequency of sine phase sound decreases with time, which means a disturbing signal. And the frequency in this graph changes from 10 kHz to 1 kHz in about 0.05 seconds, which means there's a dispersion in slinky, and I will focus it in my further theory part. And we found several periodical disturbing sound in each sine phase sound. The delta T at function left, shown in this picture, is around 0.02 to 0.07 seconds, and the time between sine phase sound is constant. Periodic is about 0.5 to 0.9 seconds, shown in this figure. And so let's ask the key question: where is the source of sine phase sound? First, I found it's a periodic sound, and then if I remove the reflection boundary, there will be no sine phase sound. And then each time when the pulse in slinky reaches boundary, as you see in the video, it's making sine phase sound. So I may conclude that the source of sine phase sound is at the reflection boundary. And now we choose periodical analysis. And first, I treat the spring as a single spring. The most important part is spring's coefficient of stiffness. And the spring's extensional deformation is actually the torsional deformation of the wire. So using that, we may obtain the torque in the wire. And then what C is torsional charge of the wire depends on the shear modulus and the geometric parameters of the wire. So then make some simple substituting, we can obtain the coefficient of stiffness as a function of number of turns, which is proportional to n. And then finally, we obtain the vibration equation of the whole spring, where the C is the deformation and the external force on unit mass such as gravity. Using this equation, we may obtain the period of horizontally slant slinky showing this formula, and the period of vertically placed slinky showing this formula. And then let's focus on the most important part, the dispersion. First, the deformation wire, there are three parts. First, distortion. Unfortunately, there is no dispersion. The next is extension. Unfortunately, it's too weak. The next remain is flexure, and I make a suppose that flexure's deformation caused the dispersion in slinky. And here's a flexural deformation, the longitudinal along this axis, and here's a wave equation where S is coordinate measure along the helix, and U is axial displacement of central in Ward's cross-section, and B is the width of cross-section. And using the wave equation, we may obtain dispersion relation and the group velocity. Finally, the delta T as function of F is L over Bg can be obtained, showing this formula. And then for another way of typing is a radial flexural deformation, where this B is a radial displacement of centroid wire cross-section and kappa is curvature of helix. The wave equation is a little bit complex, showing this formula. And finally, we can also obtain dispersion relation, the group velocity, and the small period delta T as function of F, showing this formula. So at last, we may reach the physical image of this problem. First, typing for the collision and reflection boundary produce a pulse along the wire. Then, when the pulse reaches boundary, it makes a sine wave sound because of the collision, and the delta T as a function F is exactly the traveling time of each frequency components of the pulse. And then the oscillation slinky will make periodic pulse, so the period of sine wave sound is exactly the period of slinky itself. So the torsion depends the large period T, and the flexure depends the small period delta T as a function of F. Then I will focus on my experiment. Wait for a few seconds. So I'll focus on my experiments. First, I may verify that the large period, capital T, and for experiments, I train two parts to discuss. First, when slinky slings horizontally. Then, when slinky places vertically, the formula can be shown this, and this is my experiment's results. You can see that my theory is in an excellent agreement with my experiments. And then for the spring slings horizontally, first I changed the tension, and I found the tension doesn't affect the large period as my theory had predicted. Then I changed the number of turns, and I found that T is proportional to N, and my theory is in the excellent agreement with my experiments. Then let's focus on the most important part, that's the frequency modulation characteristics of the sine wave sound. If I calculate that for each frequency, the time space between each line in the spectral graph, I found that the time space between each line is equal, showing this figure. And then I fix N and change the tension. It's obvious that if I didn't change the length of wire, that the delta T won't change as my theory predicted, which means the tension doesn't affect delta T. And then I verify that the delta T is proportional to the length of the wire. Here's my verification. Then for the dispersion relation, I measure the delta T as function of F and use exponential fit showing this formula. Then I found my theory is in excellent agreement with my experiments. Then I change the boundary condition and also for longitudinal vibration, and you see that the delta T as function F doesn't change. And then I changed the slinky and changed the geometry parameters of it, and I found that my experiment is still in excellent agreement with my theory. Then I examined the dispersion relation for radial vibration, which means I use another way of typing, and I found that the delta T as function F is exactly my theory has predicted. And then I compare the sine wave sound I produced with slinky with the real sine wave sound in Star Wars 8. And I fitted use T as a linear shift with 1 over square root of F, and I found the relate is in a good agreement. I also find another way to generate sine wave sound. typing a long steel cable about 100 meters can also make it. I found a video on internet, then I analyzed it like this sound, and I can find it that delta t is still in a linear relation with 1 over square root of f. So compare all my measurements, that we may conclude that the delta t as a function of f determines the laser-like sound, as I've said very earlier in the problem review, and the Sci-Fi sound sacrifice the delta t as function of f is proportional to 1 over square root of f. And the coefficient a, I will define it later. Then in the next graph, I use that delta t as function of f is proportional to square root of f. Then I measure, and hold on, I will show you some examples of it. If you choose that Sci-Fi sound start with 0 and ended with 0, then you make it just colliding sound as I collecting. Can you show the? And if I like the Sci-Fi sound time changes with this to this, or mean like A become larger, you will become you become the next sound, and that sound is sacrificed the real laser-like sound. If I like the sound being more longer, that I change in a large range, you make it sound, you make it like ew. That is not the Sci-Fi sound we heard. So we may conclude that the coefficient of A is exactly in this range approximately, and this is like the Sci-Fi sounds we heard. And now let's go to our conclusion. First, for physical image, technical collision can make a pulse in the wire, and then when the pulse reaches the boundary, it makes a Sci-Fi sound because of the reflection. And then the basic method we use is elastic theory, and the frequency modulation characteristics, the delta t as a function of f, or dispersion relation in the slinky determine the Sci-Fi sound. And for the larger period of Sci-Fi sound, we show this figure, it is determined by the period of free vibrating slinky. When slinky spins horizontally, showing this formula. When slinky faces vertically, showing this formula. And for the frequency modulation characteristics, the minimum frequency is around this range, and the maximum frequency is in this range, and the delta t is about 50 milliseconds. And when the slings longitudinal tapping, the delta t as function of f is this, and when the radial vibrating, the delta t as function of f can be written in this formula. And thank you. Thank you.
Okay, thank you. Any other questions by anyone?
First of all, how do you mean by delta t? What's the definition?
Delta t is showing my spectrograph.
Well, since it's different, it's depending on the frequency.
Yes.
So which frequency do you choose?
I choose each frequency, like I measure.
So in some of the graph, you didn't determine the frequency. You only show delta t too.
Yes, this is frequency, and this time I can measure it for each frequency. Exactly.
Yeah. So what do you think is the critical properties of Sci-Fi sound?
Critical.
Yes. You mentioned about the dispersion, right?
Dispersion.
And
The different people we hear the sound different, so that I said that coefficient A should be in this range that I revealed here.
So it will mean delta t should be in a range.
In range, yes, certain range.
Okay. And is the multiple lines needed?
Yes. For multiple line, in the single line in the Sci-Fi sound, for the rest of line, the sound is weaker, and that's which may determine this by the shape, not the number of the line.
Okay, you talk about the reflection of boundary.
Yes.
What do you mean by that?
Looking that the wave pulse can be reflected on boundary, and in each reflection, it will be Sci-Fi sound.
You mean that you need to tap at one of the boundaries?
No. It can travel along the slinky, and the Sci-Fi sound happens at the boundary. Or I can do the source of it as a boundary. We need to type at the boundary.
What? Okay. What is the relation between the word which is used and the wave equation? What allows to combine once we combine for separate series?
Okay, how to analyze.
Okay. You talk about like the Sci-Fi sound has some lower frequencies, right?
Yes.
So if we remove the higher frequencies, will it still be the same sound?
No. We can discuss the frequency range later in discussion.
Okay.
And I think that.
Okay.
Thank you.
So here's the problem statement. We asked us to investigate how the sound of laser shot can be produced when tapping a helical screen. And so the ideal structure of solving this problem would be first to identify the sound that is originally created by tapping a screen, and then how the sound would change while it's traveling inside the screen, which the photo said is the dispersion relations. And then is to investigate how that sound coming out of the screen into the ear and transferred into the air and then into our ears can cause the perception of the sci-fi sound, which the reporter didn't explain at all. So I will discuss that later on. And then finally, we need to determine the critical properties of the sci-fi sound through these two investigations. So these are also some parts I'm going to discuss later. So here's some pros and cons of the reporter. The pros are that I think he did clear the definition of tapping the cable screen, and he showed us some tips about the laser shot sound in the movie. So nice demonstration of the sound. And he investigated the torsion and fracture of different directions, and also he tested many parameters, and the theory seems to fit the matches with the experimental data pretty well. But the cons is that he didn't explain the difference between using he didn't clarify the assumption of using an Euler beam theory, since the Euler beam theory requires the thing to be straight, and the straight in a slinky, the wire is clearly not straight. Then we know whether this error, how does this error influence to the result? And also he didn't explain about a lot of little factors, the pixel meaning of it, and the limits of the theory. And he didn't consider the attenuation of the sound. Yeah. So overall, I think he only partly fulfilled the task in average. And these are the points I'm going to discuss later. So first is a basic understanding. Since the reporter didn't, I think that the reporter should have shown us more intuitively why is the dispersion relation related to the sci-fi sound. Since he didn't show us the spectrogram of the laser shot sound in the beginning, and I think that there are some maybe change you can do on the presentation, and it's how the initial pulse, how the initial pulse sound is like, and how it is changed to be divergent, like dispersion relation, yes. And then it's the wireless vibration model. As what I said, Euler beam theory assuming that the wire has no curvature, which couldn't be applied on the experiment. And also, he can discuss about the decay inside the screen. And then it's about the propagation error, which he didn't consider at all. But it seems that the error attenuates the sound, so some part of the frequencies might get lost. So when you are standing pretty far away from the screens, you might not hear the sci-fi sound. And I think it's really important to discuss. Also, it's about the critical quantities. Reporter talks about that the reverberation is needed as multiple lines and the dispersion relation, and about the frequency range as well. But it didn't clearly identify the temporal, like the time difference of the higher and lower frequencies, and it's really important for the sci-fi sound to hear the sci-fi sound, and how that's related to the human ear experience. So let's go to the discussion. And so first of all, first of all, let's discuss the
curvature fraction. You mean the curvature fraction?
Sorry.
Curvature fraction in your Euler beam.
Yes.
Okay. Okay, I have some appendix and I'm going to show you. And this is for the detailed calculation about the physical image in the very short. And you can see in this region that frequencies, the angular frequency, which means frequency is larger than that my series.
Okay. Where does this moment come from?
This moment comes from the references.
Okay, can you explain it intuitively?
Okay, this C is the coordinates or the deformation measured along the wire, and the S is the coordinates measured along the wire. The V is the radial displacements.
So for example,
okay. S is the coordinates we measured if there is no deformation, and the C is a deformation after the pulse is in it, and the V is the radial deformation, and both V and C is a function of the original coordinate and the function of t.
So these two terms are the whatever we between, right?
Yes, yes.
So where does these come from?
Where this come from? If you write the deformation of a single disk, and for the rate of deformation, if you suppose
Give me a short answer, please. Short answer. Intuitive answer.
Lagrangian.
Lagrangian?
Yes,
So you can analyze the energy of this?
yes.
Okay, well, I think a much more intuitive answer would be that since the whole thing is curved, because this term is all related to the topological curvature of the
Yeah.
so this will only exist when the string is curved.
Yes.
So I think that is like much probably related to the displacement on this direction will contribute to the displacement on this direction as well. Yes. So
And my function is a coupling. And I can also clarify it that you consider that if the red line is that you might prevent more simple theory, and the blue line is for the correction. And you can see for the group velocity as a d omega over dk, that didn't change in the this range.
okay, I think that you should have explained much more clearly about like this theory here.
Okay,
Because since you use it but you didn't explain it at all.
Okay.
I think
Okay. My theory is a
it's
pre-PowerPoint.
okay. It's okay.
All derived by myself. I didn't look at any references.
Okay, so but you use this as a
This is
correction.
as a reference,
Yes,
as
so
appendix.
yes. That's my thought. Okay, let's jump to the next part. So let's talk about like the spectrum.
Okay.
So with this thing sound like the sound.
Yes.
Only one line. Will it sound like a Sega sound?
Yes, I may sound.
But do you say that you should need to be multiple lines?
No. I can show you my simulation.
No, just tell me, would this sound like a Sega sound?
Yes.
Okay. So the reverberation is not PD.
What means reverberation?
The reflection.
It is in the real situation, but if you only have this curve, you may just correct them down. Let me show you. I think it's very interesting part to discuss.
Okay, it's okay, it's okay. Let's keep on the discussion. Okay, all right.
Okay.
Okay. So if the line is like more compressed, will it still sound like a Sega sound?
What?
If the line is like compressed in this direction.
I won't discuss with you. I think it's interesting. So let me show you some of my.
Just your opinion, yes or no?
No. So this thing should be a certain range. As I showed you point twice, the coefficient A should be in a certain range that we can hear this sound and the sound is
Okay,
sound.
so
If it's too short, you will just feel like this sound. And
you mean this range?
yes, it should be a certain range.
Okay, so like for example, this is 5K.
Yes.
1K.
Okay.
What should be this range mean?
5K is not enough.
Okay, and 10K.
About 100 milliseconds.
Okay, how can you explain it?
Explain it by our ear. That our ear heard that we can only hear if this sound change very fast in a certain time. Our ear cannot just hear it. We cannot identify it.
Okay.
If it is a certain range, we can partly identify it and heard it like the sound.
Okay, so I think a much clearer explanation would be like the human ear would have a temporal distribution about like distribute.
It is show that this
the
is for the
difference
time is
about-
very short, and this is for normal time.
Okay.
This is for large time. You can find the difference between it.
Okay, so I think a much more clear explanation would be if it is too small, then the ear's temporal distribution is not big enough to differentiate these two frequencies coming.
Yes,
Right.
it is because our human that
Yes,
if
I know.
use detector,
I know. I just want a more easier to understand explanation. Yes. And if it is stretched out, will it sound like a sound?
No, like that. The only first part like, but in the second part too is not like sound.
Well, I think like still a much more intuitive explanation would be like for example, if you play a piano, so like if it is too stretched out, then it wouldn't sound like a single sound, right? It will sound like a furious.
Yes,
You know?
but if we should only hear the first part like that sound. If the rest of the part is not like, it would affect us.
Okay. So I think that there are some like you should have defined like this range of the time difference of the higher and the lower
This
frequency.
one is showing this formula. That the coefficient A that defines that the range that you saw.
And you also define another time difference about this, right?
Yes.
How is this important?
If this is if show my spectrogram is like this, and this is all the same, and which is this exactly means the traveling time of the pulse.
Okay, but is that directly related to the Sci-Fi sound?
Okay, I know that. So first, the spectrogram this line means the tapping.
No, I understand is a reflection.
And I measured this like this 4 delta GT, Wi-Fi 4 is this, so I can measure this more accurately.
But how is that important?
If this spectrogram are vanished, we will still hear the view sound.
Yes, so I don't think that this is important.
This is very important. If you change the delta X function app, you won't hear it.
No, like for example, like you have the same line, but
Yes.
you just like originally you have this, and you put it like the same line, but you put it like the shape of the line is the same, but the difference in between is spread out.
That I mean that the shape of this, the delta T for this is equal. If you change this delta T will also change too, and you won't hear the sound.
Well, then I think that the most important aspect of this line will be this difference.
I mean that the delta T function app is equal for each frequency.
Okay, that's it. Okay, so do you think that the sound traveling through air will the harmony of it will change?
Well, no, I heard it from the 50 millimeters and change, and if I just detect or sound it will be not changed.
Okay, but you know that sound will attenuate in the air, right?
Yes.
Yes, and the different frequency will attenuate at different rates.
Yes.
The lower frequency will be attenuated like.
I think that frequency range is very important in the wave transfers in the syncing. Let me show you my appendix.
Just give me one range of the frequency you need is needed. Just give me a range. A range.
Yes, that is, we may suppose, first, let me explain the question for you.
Just give me a number, a range of frequencies.
1 to 10, approximately.
You mean kilohertz?
Yes.
Okay. And so you will remove. Can you explain why do you remove the upper part? What sound like?
I will explain. The sound intensity is proportional to the initial amplitude and the radiating power is related to the force power of F and the absorption sound. You may find the absorption.
Intuitive explanation.
Because the high frequency causes more absorption.
So
Higher frequency causes no, in the slinky itself.
Okay. So I think that you should have like expressed it in your report. You didn't say it right. The decay in as I wrote here, the decay in the intensity is happening. So it's important to the frequency. Okay. So okay, finally, you talk about delta T, and I really think that the delta T is not important because that is too much related to the length of the string. I think that's much more of a better way to present it by the velocity, the true velocity.
I measure delta T as function that is, we just measure delta T. You can use delta T as L over delta T as VG. Okay, that's
but it is related to the L, so I don't think it's X.
I changed L and found the delta T is proportional to L. I think it's.
So yeah, overall I think it's more important. So okay, that's it for my post. Thank you.
Okay, may I ask the opponent to summarize the discussion?
Okay. So in my discussion with the reporter, I talked about the vibration model, the limitation of the ROUND3 since it is assumed to be a straight bar. So we did some correction on the closure, and I asked you to explain those corrections, and I did my own opinion as well. And I think that the reflection on the wave isn't that essential to the properties of Sci-Fi sound. And then to talk about the intensity decay inside the string, which is related to the frequency range needed for the Sci-Fi sound to be heard like the Sci-Fi sound. Also, here we talk about the time gap between the higher and the lower frequencies. And I think that the reporter should have mentioned that the higher and lower frequencies, the time difference between those two should be in a certain range, which is related to the properties of the human ear. And also, we talk about the frequency range, which I agree to respond is really important. Thank you.
Okay, thank you. 3 minutes time for the reviewer to ask questions.
First, to the observation. How do you think the sci-fi sound is made intuitively? Oh, to the recorder, sorry.
What? Pardon?
How do you think that the sci-fi sound is made intuitively?
Made because of the division of the boundary and slinky.
Okay. What actually causes the sound intensity? What causes the sound to be more intense or less intense?
The amplitude and the matter which produce sound.
What is, yeah?
I think it's pretty much related to the original tapping force.
Okay. Did the reporter take into account, to the reporter, what causes the extra reflections or echoes? What do you believe causes the extra reflections? In the frequency versus time curves, what causes the extra reflections?
You're tapping in a place and the wave, the time that wave tries to one to another point is different. Its time is different, so it calls the frequency as function time.
What do you agree? What was to the reporter? What was the range of frequencies observed?
Approximately 1 kilohertz to 10 kilohertz, approximately.
Why did you assume that the torsional and extension did not cause the sound?
Torsional and the torsional causes the vibration of the slinky itself. The frequency is about 1 hertz, and the extension is very weak.
Did you actually measure or get numerical?
That I just showed my planning that extension, if it's at extension coupling with friction,
Numerical. Do you have numerical value for what is too weak?
showing that the dispersion relation is the extension doesn't affect the dispersion relation. I show my appendix.
How was the background noise removed? The reporter. Reporter. Do you have an idea on what theory can be used instead of the curve
A wire. I think he's thinking about considering the curvature is nice. It should be able to apply, but you need some explanation about it.
to the reporter. How did you actually analyze the data of the frequency time curves?
For each frequency, I counted the delta t from each spectrogram or the first line that tapping and this curve line.
And what were the error bars for? Like, were they between trials?
The Y's of were caused by my computer.
How many trials did you take for each experiment?
For experiment, I counted 20 points.
But did you repeat the same?
Yes, I counted for each spectrogram for about 5 or 6 times, and I found the error bar is like around 73 to 75 milliseconds.
Okay, thank you. Please proceed to preparation.
Okay, we start with me.
Good afternoon. I'm Christopher from Team Australia, and I'll be reviewing Sci-Fi sales. I will first be going over the overall presentation of the report and the comment, then the presentation of the report, the presentation of the opponent, and the actual discussion. First of all, the report. They modeled quite well both the torsional and longitudinal vibrations. They had a great use of sounds in their presentation, which was done quite well. They tested quite a few parameters and plotted their experimental versus theoretical graphs quite well. Some areas for improvement. They misunderstood what the source of the actual sound was. The source is simply the mechanical vibration present inside the slinky created by the tap. They spent too much time talking on reflections and did not actually talk about how the sound is formed. It's because faster frequencies travel faster in a dispersive medium, slower frequencies travel slower. That's what creates the actual sci-fi sound. High frequencies travel faster, sorry. They did not actually give a mathematical definition of what a laser Simon shot was. In their setup, the slinky was held vertical. They did not explain what the effect of the slinkies bunched up on the ground and the reflections through the ground would be. They did not actually go through why dispersion occurs or what it actually means and how that affects the sounds. They did not define what too weak of an extension meant numerically. They plotted time against frequencies instead of frequency against time, which is quite hard to follow. And they did not talk about the assumptions they made during their model. Onto the reporter, he picked up that the source was from tapping and not sound traveling into a different medium. They picked up that the constants were not experimentally determined and mentioned the lack of stating actual assumptions. Areas for improvement was that during the clarifying questions, they sort of stepped into discussion and were not actually clarifying some stuff. They did not pick up on the lack of error analysis that was present in the reporter's presentation, who did not actually get numerical errors or explain the discrepancies between theoretical and measurements. Again, the reporter did not actually ask, did not get a physical explanation of dispersion. The very basic physics explanation was not asked for and not put into their discussion. So first of all, they explored the temporal, the opposition went into the temporal resolution where the reporter believed that the Sci-Fi sample is based on a range of frequencies which is perceived differently within our ear. We agree with the opposition that if the sound is too short, our ear will not pick up the differences. And we believe that too much time was spent talking about this when they did not dive into the basic physics explanation of dispersion. The opposition picked up that on the incorrect assumption of the Euler-Bard beam theory. The reporter believed that their added factors were not correctly modeled in, but we agree with the opposition, and that the curvature of the slinky is important, and that the modeling could have been improved further. Overall, I think the discussion, they wasted too much time on unimportant factors. They did not they did not address the efficient points in time or the actual production of sound. They both kept going back to mathematics instead of intuitive physics of why higher frequencies travel faster and why slower frequencies travel later on. Our opinion was that the importance of the physical explanation of what causes the Sci-Fi sound is extremely important. And we believe, that's it.
Okay, thank you. 2 minutes time for concluding remarks by the reporter.
Now I give the reporter's conclusion. First, I thank the opponent and reviewer for their suggestion and advice. First, for the question they asked, first for the curvature of the spring, I show that in this formula is for the radius evaporation, and the curvature is exactly shown there. It's very important. I show in my theory. And for the delta t as a function map, I believe it's determined the laser-like sound. And for the spectrograph, this is for the first part of my typing, and this is for the delta t, the 2 delta t paths, 2 delta t, 2 delta t, and all this in the same spaces. And if there's no these two lines, there will be still a Sci-Fi sound. This is my opinion of it. And for the reviewer says the extension is too weak and I cannot prove it. I've shown it in my appendix that the two lines, the red and blue, that the dispersion relation did not even change. And I think that if I didn't consider the extension, it should be more clear physics image. And next, I want to clarify that the all theory in the 12 minutes report I give, except this appendix, is all derived by my own. And then now I will clarify conclusion. First, I believe that the Sci-Fi sound is caused, the dispersion is caused by that the wave, if we type in the left side of the slinky, that the traveling time of each frequency components will be different. While each component reaches boundary, it will produce the Sci-Fi sound. So it calls the frequency as function time or minute disturbing. It's the basic characteristics of the Sci-Fi sound. And then for the frequency range, I use the absorption model to explain it, and I explain that the Sci-Fi sound defined mathematically as that delta t proportional to 1 over square root of f, while a should be the region I've given shown in my report. And for the torsional, it's torsional deformation. It is just for the vibration slinky itself. It produces a continuous pulse. That's all.
Thank you. Sorry, 5 minutes time for jury questions. Yes, Martin, please.
So on that slide you were showing, can you just briefly explain on that slide in the conclusion? Before, when you had those small delta t,
Yes.
can you just briefly remind me the origin of the other lines that were there?
Just because the pulse which is there and reflected to there is still line. At each reflection there will be a line, but the most we can.
Like there is this capital T and small t. So can you
small t.
yeah, small t.
Kind strong. This is small t, and for this is capital T. Each time is
I understand, but like, what's the origin of the other lines that are spaced by delta small delta? Yeah, those. What's the origin?
Capping at this point, the pulse travel to this, having a sound, and it reflect to there, also having a sound, reflect to there, also having a sound, but the intensity getting weaker.
Also, capital T is the decay.
No, the capital is not. Capital T is caused by the vibration of slinky itself, which I mean that the pulse is slinky. First, the vibration will produce pulse, and also I produce pulse because of the collision of the vibration itself at this time, and this pulse travel very faster. That's just environment this travel a lot of time and produce a small delta T.
Yeah, and the
Sorry,
big ones are
there's no more time for any
sure.
clarification. Susan was first.
No, that's the reporter. How is a sound made at a boundary? Can you tell me how the physics of this works, please, briefly?
The pulse collide with the boundary and make a sound. I can prove it experimentally that if I remove it or use just some substance to make it won't produce.
Okay, Jacob?
Can I ask the other two what they think?
Yeah, so the sound is the energy that is transmitted through tapping, creates vibrations. That is what the actual sound is. The Sci-Fi sound is heard because the slinky is a dispersing material, which means that.
Okay.
Oh, so basically, it's where different frequency travels at different velocities. So the high frequencies which they reach and go there and come back quicker. So
Okay, Jacob?
Yes. Can you please show us your reference list for this report?
Only the first part of all this. No, not for appendix. I derived all this by myself.
Okay, so you claim ownership to all the theory that was presented
Yes.
here.
Yes.
Thank you.
My teacher told me about the basic thing I just derived.
Okay. Question from my side. Yeah, to the reporter. Does the theory apply mostly to transversal or longitudinal modes, and how do we experimentally make sure to excite the one or the other?
The transfer that for the longitudinal is extension of deformation. It won't produce sound, and the frequency of it is very high. That we cannot hear it actually, and it's also too weak for transverse wave.
The transverse waves won't produce any sound.
When it's collided, it will produce sound. When it's transverse in the air, it won't produce sound.
Okay.
No, for this thing itself.
Jacob?
Yeah. So question to the reviewer. So you asked for a mathematical definition of a laser shot. Could you please provide such a definition?
What's it?
You asked for a mathematical definition of a laser shot. Could you please provide us with such?
Just like what one single curve as a frequency versus time will look like, as in when do the different times are like how do the frequencies have to be different from each other for us to interpret a certain sound as a laser sound?
Thank you.
Yes, something like basic relationship between frequency versus time difference in us here.
Okay. Question to the opponent. You asked why we see multiple lines like the ones drawn on the board, right? I didn't quite get your opinion on that. How is it possible to observe multiple of those lines?
well, the lines come from the reflective waves. So the first pole will be a straight line, and the first reflection is one curve and then more curve.
So that's the reflections.
Yes, but my point is that the reflections aren't critical for Sci-Fi sound to sound like a Sci-Fi sound. That only one curve can also sound like Sci-Fi sound.
Okay, thank you. Yeah, follow up by the reviewer?
Go further on that.
Yeah.
It depends, because if their experiment was controlled to just provide the force in one particular direction, then yes, it would be just the reflections. But if it was not controlled how the actual tap was done, it could have been vibrations in multiple directions that are traveling at so like they have a different model, the transverse versus longitude.
Okay, thank you. And I guess that is it, and we'll move on to Brenda. We show our marks for the reporter, please. That's mostly consistent. It's 7, 8, 7, 7, and 7.
Thank you.
For the opponent, 6, 7, 7, 6, 6. And for the reviewer, 6, 3, 6, 7, and 7. So that's quite consistent this time, except for the review. So for the report 4718, so I would invite anybody to comment.
Yeah?
Jacob, go
So
ahead.
I have to comment on this because to me, this is the clearest definition of a 9 MC. There's just a key problem here, and it is that if you just Google on like the basics on this problem, you find a number of papers with more or less the very similar theory to what you just presented, and I find it unlikely that they would just now randomly show up. So had you showed a proper reference list and given proper reference to what you've used, I would have put a 9. But as you answered to me deeply incorrect on that, I put the maximum negative score I can give for that, which is 2. So my partials were 6.2, 2, and then -2 because of that, and that ends me up on a 7.
Okay. From the report itself, I would like to add a short comment to that. I felt like the theoretical derivation was mostly correct. So my understanding of the problem, it was completely feasible on tackling the problem. However, I found the experimental analysis was rather the weak part of the overall report, because I believe that you should have tried to go one step further and not just do a visual comparison on the line, but try to systematically extract the maxima of the tracks you see, and try to have an analysis that is mostly based on any sort of reproducible analysis rather than comparing it visually yourself. And going along with that, I mean, you had a fit coefficient beta that was your exponent basically, but you claimed that the exponent was pretty well known for theory. So basically fitting an exponent that should be known and fixed by theory should not be allowed in this case. And there was one slide where you could actually see that the curvature of those 1/f square lines was, or the asymptotes were, it seemed like the asymptotes were even different. And that is what happens when you fit like visually rather than mathematically. So I would have liked to have to see that in a more proper way. But this is most of the negative for the report.
Just like a slight comment, I had to sometimes think really hard on which experiment are you currently showing us, which setup, you know, how, if it's radial or the other one. That was like the weakest mark for me, the partial mark. Like this column was the weakest for the report. Like overall.
So science communication.
Yes, science communication.
Okay. Yeah, I agree to that. It's also the weakest on my sheet. Okay. Okay. For the opponent, let's see, 2 7s, 3 6s, same game. Open for comments. Jacob?
We have to start on the 6 again. So this was a very, very hard opposition to judge, because I thought that your speech was excellent. So for questions I gave a 1, because some of them were relevant but not too many. But the speech I gave a 3, almost considering giving it a 4, because you brought up so many good things. But I could hardly understand anything about what you were discussing. So it was a problem with structuring theory. If I can't understand, I can't grade the time. So I gave it a 1.4, and that was partially because the reviewer kind of saved you by actually pointing out like what you were actually talking about. So that was the problem for me, that I didn't understand what you were discussing. So then I ended up on a 6.
I fully agree to that.
I did as well.
Yeah. So I like your strong points, like asking for the assumptions of the Euler beam, and actually claiming the limits of the equations, because that would have also been interesting things to be discussed. But I kind of, like Jacob, I also got lost in the discussion because I didn't actually manage to get a full view on actually your own opinion, because you somehow didn't state it clearly enough. So next time you do opposition, please state your opposition clearly. That would have most certainly given you a higher mark on my sheet. So I have a 1 for questions for the same reasons as Jacob. I have a 2 for the presentation, and I have a 1.5 for the discussion, which is a 6 in total. For the reviewer, we have a low 3 by Martin.
Yeah. For me, I was deciding between 3 and 4 at the end. Partial marks were somewhere around 1/2 to 1 all over the time, because I couldn't quite, like the points you were making, most of the negative ones weren't really relevant for me. So you, for example, stated that T versus F was different, or you started saying that the dispersion wasn't, I mean, it's partly true, but I don't think that was the proper review of what I've seen. If you just, and if you just like state all the things that were missing in phenomenon explanation, that's not the whole presentation. And I could not feel any prioritization of what was the most important part of the presentation, what was the worst thing probably. And that's this thing just went on through the whole review. And sometimes I think for some of your questions they were like not very well managed. They were not conducted very well. I think sometimes I didn't hear the answer for some question, and that also resulted in relevant meant to clarify unclear points marked for question asked.
Okay, 7th by Jacob and Susan.
Yeah, so I think we have to start coming. So I really liked a lot of the review, in particularly because while, as I say, I felt quite confused after the discussion, you really tried to, okay, what's the basic physics going on here, what's happening, why is things different, and so on, and try to really sort up a lot. And as I say, you did a great, review of opposition by definition was great because it actually allowed me to understand what I should grade and not should grade. And what I did not like, however, is I have a strong affinity against when team says, oh, for example, a definition should provide of this or this, and then cannot really provide a proper definition of themselves. In my opinion, sci-fi is not like a laser shot is not a mathematical term. A laser shot is kind of a intuitive thing like we hear on a sci-fi movie, and I fully agree with the reporter's approach to show us some of them and then show that he can reproduce a similar effect. So I don't think we should interpret that as a mathematical concept, and hence I subtracted one for that.
Yeah, one tiny add up for this. I like you claiming that like time and frequency should have been clearly separated when actually measuring and putting that on graphs, because I also felt like it was hard to follow because time and the delta t, capital T, and frequencies were like messed up into one another, and so it was very hard to follow. And I like you pointing out that tiny formal aspect, because that is part of your role as a reviewer. I like that very much. Okay, if there is no more justification needed, I would ask you